Okay, so welcome everybody to the new session of the European Non-Associative Algebra seminar. And today it's my great pleasure to introduce a brave new doctor from the University of Santiago de Compostela, Andrés Pérez-Rodríguez, who is going to talk about lattice-theoretical aspect of evolution algebras. So please, Andrés, go ahead.
Good afternoon, everyone. First of all, I would like to thank the organizers for the invitation and also Professor Viruel for introducing me. Today, I would like to present part of the research I carried out during my PhD under the supervision of Manuel Ladra in the University of Santiago de Compostela. And as you can see in this first slide, we are going to deal with lattice theoretical aspects of evolution algebras. So the main goal of this talk is to give an overview of some structural properties of these algebras and to explain how the lattice of subalgebras can provide useful information about their algebraic behavior. However, before discussing the main results, I believe it is important to briefly explain the origin and motivation of behind evolution algebras. So the starting point of our work is the study of population dynamics. Growing environmental pressures such as climate change, habitat loss, or biodiversity decline have increased the need to understand how ecosystems behave. Actually, ecosystems are highly complex and highly interconnected systems where different species interact in a non-trivial way. In this context, Barry Commoner formulated one of the fundamental laws in ecology, namely everything is connected to everything else, which means that although ecosystems may have their own mechanisms that stabilize them, at the same time, small perturbations can be amplified and produce large long-term effects. For this reason, understanding how biological populations evolve over time has become a central problem both in ecology and in mathematics. But to better address this problem, we first need to recall what we mean by a population. A population is defined as a group of individuals of the same species that live in a given geographic region and can reproduce with each other. When we try to analyze their evolution over time, we have to take into account several key factors such as the survival rate, the reproductive success, the distribution, or heredity. From a mathematical point of view, we have several mathematical tools we can use to model all these phenomena. For instance, stochastic processes, dynamical systems, or difference and differential equations. However, in our research and also in this talk, we are mainly interested in an algebraic approach to this problem. So one way to do this is through generic algebras. Generic algebras were introduced by Etherington in the 20th century, and they arise with the purpose of modeling inheritance. And the key idea behind them is very simple, sorry. All the possible genotypes of our population are represented by the basis elements, and then the reproduction is encoded by multiplication rules. So extending those multiplication rules by bilinearity gives rise to the desired algebraic structures. In fact, generic algebras are typically non-associative, and moreover, they do not fit into the classical framework of algebraic varieties because they are not defined by polynomial identities in general, like Lie, Leibniz, or Jordan algebras. In the literature, we can find several types of or classes of generic algebras, for instance, gammetic algebras, théoric algebras, Varick algebras, Bernstein algebras, even more recent options like gonosomal algebras, but in particular in this talk, we will focus on a specific class called evolution algebras. Evolution algebras were introduced by Tian and Vojtěchovský in 2006, and they arise with the purpose of modeling non-Mendelian inheritance, which is actually considered the basic language of molecular biology. They mathematically formulate the process of asexual reproduction, and the idea behind them is very simple because its construction is based on the self-replication rule of non-Mendelian inheritance. This means that two different genotypes never interact because we are considering asexual processes. So their product will be taken as 0, while the product of an element with itself, that is its square, will describe the probability distribution of the offspring when the corresponding genotype reproduces, divides, self-replicates, or whatever. It's important to mention that although this is quite nice to motivate and as a brief piece of history, but we are not interested in making any kind of biological interpretation, so it's time to present a formal definition of evolution algebras from an algebraic point of view. So an evolution algebra over a field K is a K algebra that is simply a vector space with a product, which admits an special basis called natural basis, such that the product of two different elements of that basis is always 0, while the product of an element with itself will be a linear combination of all the elements of the basis, right? So using this definition, it is straightforward that the main characteristic of evolution algebras is that they are completely controlled by the squares of the elements of the natural basis. Moreover, they are commutative but non-associative algebras in general. And something important is that all algebras considered throughout this talk will be assumed to be finite dimensional. All these coefficients omega ik that I have here can be arranged in a matrix that will be called the structure matrix of the algebra. It is important to note that if we were interested in making biological interpretations, then the structure matrices would have to be stochastic, but as it is not the case, we will consider matrices over a field in general. So I decided to divide this talk into 3 parts, which follow closely the chronology of our research. All parts concern subalgebras of evolution algebras, but from different perspectives. In the first part, we will focus on the very specific case of regular evolution algebras, and we will show that in this case, subalgebras enjoy a particularly nice property. Then in the second part, we will study subalgebras through another theoretic perspective, because we will try to study the structure of an evolution algebra through the properties of its subalgebra lattice. And finally, we will focus particularly on maximal subalgebras through the framework of Frattini theory, which I will introduce and explain later in the talk. So let's go with the first part. And of course, we first need to know what we mean by a regular evolution algebra. An evolution algebra is said to be regular or perfect if it equals its square, meaning that it is also generated by the squares of the elements of the natural basis. Moreover, as we are working in the finite dimensional case, these algebras are quite easy to identify, because an evolution algebra is regular if and only if its structure matrix is non-singular. And I have to say that they are probably the most studied type of evolution algebras, and in fact, they enjoy several nice properties. For instance, they admit a unique natural basis. If we consider different natural bases, then all bases will be the same up to permutation and multiplication by non-zero scalars. Their automorphism groups are always finite. Their ideals are basic. This means that their ideals are directly generated by the elements of the natural basis without needing to consider linear combinations of them. And they also have a very interesting property, which is that they are universally finite. This means that given a finite group G, we can always find a regular evolution algebra such that its automorphism group is isomorphic to G. So to understand our main contributions to these, our main contribution concerning regular evolution algebras, we first need to highlight that one of the main weaknesses or challenges when working with subalgebras of evolution algebras is that in general, they do not necessarily admit a natural basis. That is, subalgebras of evolution algebras are not necessarily evolution algebras again. So we proved that in the regular case, every subalgebra admits a natural basis. So in the regular case, evolution algebras are closed under subalgebras. So here we have another nice property we can add to the collection of nice properties of these algebras. And although I don't want to talk very much about the implication of this theorem, I would like to say that it helped a lot when we try to characterize the existence of certain subalgebras and also predict their structure. But unfortunately, it didn't help very much when we try to analyze their subalgebra lattices, mainly for the next reason. For instance, consider these two evolution algebras. Both are regular, and trust me, they are very similar from an algebraic point of view, because most of the invariants that we normally use when we study evolution algebras coincide in both cases, but they differ in only one structural constant. And as you can see here, their subalgebra lattices are completely different. In fact, our research focused mainly on two properties, as we will see in the next slide. And the first one satisfies both properties, while the second one satisfies neither of them. So since the regular case is difficult, we decided to focus our investigation on solvable evolution algebras. But before starting with our main results, I think that it is important to mention that lattice structures have already been extensively studied in a wide range of algebraic settings. The most classical example is the case of the lattice of subgroups of a group. But in the literature, we can also find investigations about the lattice of right ideals of a ring, the lattice of submodules of a module, the lattice of ideals in associative algebras, and even in non-associative contexts, like the lattice of subalgebras in the algebras. However, this type of studies had not been conducted in the context of generic algebras, and in particular for evolution algebras this problem was completely unsettled. So as I said before, we focused our investigation mainly on two properties, two classical lattice-theoretical properties, namely distributivity and modularity. As you can see in this slide, they are defined by the distributive laws and the modular law respectively, but I don't care very much about them, because in the next slide we will see some better characterizations that will be more useful and instrumental for us. But first, let's see some examples. Using these laws, it is easy to check that chains are both distributive and modular, that diamonds are not distributive, but they are modular, and that pentagons are neither distributive nor modular. In fact, the last two lattices are essential when characterizing these two properties through these two results I have here. First, we have this distributivity characterization of Virchow, which says that a lattice is distributive if and only if it does not contain a diamond or a pentagon as a sublattice. And in a similar way, we have a modularity characterization of Dedekind, which says that a lattice is modular if and only if it does not contain a pentagon as a sublattice. So using these two results, it is straightforward that every distributive lattice is also modular, but the converse is not necessarily true, and the diamond is an example of that. Okay. So we started our research by considering nilpotent evolution algebras mainly for two reasons. On the one hand, nilpotent evolution algebras are perfectly characterized by this result of Casas, Ladra, Omirov, and Rothikov that I have here, which says that an evolution algebra is nilpotent if and only if the natural basis can be reordered. In such way, the structure matrix is strictly upper triangular. So when working with nilpotent evolution algebras, we can assume without loss of generality that the structure matrix is R of this form. Moreover, we also have perfectly identified when the maximum index of nilpotency is reached. In fact, it happens if and only if this strictly upper triangular structure matrix has no zero in the first upper diagonal. And on the other hand, we also have classifications of nilpotent evolution algebras in low dimensions. In fact, we used the classification of three-dimensional nilpotent evolution algebras, and we constructed explicitly their subalgebra lattices. So once we have all these lattices constructed, it is easy to characterize modularity and distributivity simply by looking for diamonds and pentagons inside of them. But of course, this is not a general result. But sometimes studying what happens in low dimensions can provide insight into the higher dimensional case. And that is exactly what happened here. Note that the only distributive lattice here is the fourth one, which precisely corresponds with an evolution algebra with maximum index of nilpotency. And this result can be generalized to any dimension, as shown in this distributivity characterization theorem. If we have a nilpotent evolution algebra of dimension n, then the following assertions are equivalent. The algebra has maximum index of nilpotency. The subalgebra lattice is a chain of length n. The algebra is distributive, and moreover, the algebra is cyclic in the sense that it is generated by the first element of the natural basis. It is important to mention that this last condition is an analog to Ore's theorem for group theory, which says that the subgroup lattice of a group is distributive if and only if the group is locally cyclic. Unfortunately, the study of modularity was not that easy, and we had to use this result here of Anqueda, which had been already used in both associative and non-associative contexts, and it states that if we have a finite dimensional nilpotent algebra, then we have an equivalence between modularity, upper semi-modularity, and the fact that every subalgebra is a quasi-ideal. This means that given any pair of subalgebras, the subalgebra generated by their union corresponds exactly with their sum as vectorial spaces. Here below, you also have the definition of upper semi-modularity, just if you want to look at it, but I don't care very much about it because I won't use it throughout this talk. I only want you to know that it is a weaker condition than modularity, and that in this case, both are equivalent. And although this result may seem important, let's say, because it characterizes modularity in some sense, in our opinion, is not good enough because it doesn't give enough information about how these evolution algebras are or any conditions on their structure matrices. So using this result, we proved this necessary condition in the nilpotent case, which says that if an algebra is modular, then there are no absolute nilpotent elements outside the annihilator. An element is said to be absolute nilpotent if its square is 0. And something important about this result is that we have to be very careful with the ground field we are considering. For instance, if we consider this evolution algebra, whose product is E1 square equals C2 square equals C3 and E3 square equals 0, if we consider it as an algebra over the complex numbers, then it admits absolute nilpotent elements outside the annihilator, so it cannot be modular. But if we consider it as an algebra over the real numbers, it does not admit absolute nilpotent elements outside the annihilator, and in fact, it is not modular. It is modular, sorry. Something which is also important is that the converse of the previous result is not necessarily true. For example, if we consider this 6-dimensional evolution algebra, it is easy to check that it has no absolute nilpotent elements outside the annihilator, because E1 square, E2 square, E3 square, and E4 square are linearly independent. But if we define these two subalgebras, U1 and U2, consider the subalgebra generated by them, then we obtain something a bit bigger than their sum as vectorial spaces, so they are not quasi-ideals, and consequently the algebra cannot be modular. But why this example fails? Why this necessary condition is not sufficient too? Mainly because we were not taking into account that modularity is a property which is preserved under quotients. Maybe in the very beginning, an algebra does not have absolute nilpotent elements outside its annihilator, but if we consider some quotient algebra of it, those absolute nilpotent elements may appear. And that is exactly what happened in the previous example, where E1 plus E2 plus E3 was not an absolute nilpotent element, but if we consider the quotient by the annihilator, it becomes an absolute nilpotent element. Finally, this problem was not very difficult to solve, and we were able to characterize perfectly modularity on nilpotent evolution algebras over quadratically closed fields. In fact, these evolution algebras are going to be modular if and only if they can be written as a direct sum of something with maximum index of nilpotency and something abelian, where abelian means that all the possible products are 0. So once modularity and distributivity are both characterized, we try to obtain also results in the more general setting of solvable evolution algebras. Recall that nilpotent algebras are also solvable, but the converse is not necessarily true. And I have to mention that studying solvable evolution algebras is much more difficult than the nilpotent ones, because we don't have characterization results or a classification in low dimensions, for instance. But something that we do know is that our result of Ankela also holds in the more general setting of solvable algebra, so we can continue using it, okay? So as we don't have a classification or a characterization result for solvable evolution algebras, we decided to focus mainly on two families of solvable evolution algebras. First, we have solvable evolution algebras with one-dimensional derivative algebras. This family was originally introduced by Camacho, Gomez, Omirov, and Turdivaev, and they will be denoted by TK because they will appear several times throughout this talk. So the key point of these algebras is that in a certain natural basis, the first k columns of their structure matrix are the same, while the remaining columns are 0. So consequently, all the squares of the basis elements are scalars, multiples of the same elements, which explains why the algebra has a one-dimensional derived subalgebra. Moreover, we also require that the sum of the first k lambdas must vanish, and this is precisely what ensures that the algebra is solvable. And maybe it's a bit odd, this characterization, but I think that with an example, everything will be clearer. Consider, for instance, this four-dimensional evolution algebra, and note that all the squares of the elements of the natural basis are a multiple of E1 plus E2 plus E3. So the corresponding structure matrix is this one. And as stated before, the first three columns are the same, while the fourth column is a zero column. And in fact, the sum of the first three lambdas, 2 plus 3 minus 5, vanishes as required. So in this family, it was quite easy to characterize these two properties. In fact, we obtain an equivalence between modularity and distributivity, and we also deduce that they only occur in very low dimensions, more precisely only in 1 and 2 dimensional evolution algebras. Moreover, we also prove that any direct sum of these algebras is neither modular nor distributive, and they satisfy many more properties that we will see later. Okay, so on the other hand, we also try to obtain results concerning evolution algebras with maximum index of solvability. When we studied the nilpotent case, you will probably remember that evolution algebras with maximum index of nilpotency appeared several times. So we wanted to check if we can also obtain results concerning this more general setting. And to understand our main result, we first have to recall the definition of supersolvable algebra. An algebra is said to be supersolvable if there exists a complete flag made up of ideas, that is, there exists an ideal of each dimension and each ideal is contained strictly in the next one. This property had been already used in lattice theory because it is a sufficient condition for lower semi-modularity, which, as you probably imagine, is the dual property of upper semi-modularity, and again, it is a weaker property than modularity. But the most important thing here is that we were able to characterize supersolvable evolution algebras as follows. If we have a solvable evolution algebra, then it is supersolvable if and only if every quotient algebra, has a non-zero annihilator, or it has an ideal isomorphic to an evolution algebra of our family TK. So roughly speaking, we have that the algebras of the family TK are like the building blocks of supersolvable evolution algebras. So now we arrive to the main result of this part. First, if an algebra with maximum index of solvability is modular, then we obtain a strong restriction on its derived series. There cannot be two consecutive terms in the derived series that fail to be basic ideals. So the derived series has to behave in a very controlled way, right? What is remarkable is that this condition turns out to be equivalent to supersolvability, and this allowed us to prove that these three conditions are essentially equivalent, except for a pathological case, which I won't explain here, okay? So let's go with the third and last part of this presentation. But first, of course, we need to know what we mean by Frattini theory. Frattini theory was first introduced by Giovanni Frattini in 1885 in the context of group theory. And he defined the Frattini subgroup as the intersection of the maximal subgroups. This Frattini subgroup captures the notion of groups non-generators as it consists precisely in all those elements that can be removed from any generating set without losing the generation of the group. Moreover, it has several nice properties. For instance, it is always a characteristic subgroup and consequently it is normal. Moreover, the Frattini subgroup of a finite group is nilpotent. And finally, it also serves as a criterion for nilpotency because it contains the derived subgroup if and only if the group itself is nilpotent. So these nice properties make this Frattini theory to be extended to the framework of algebras. In fact, nowadays we can find well-developed Frattini theories for Lie and Leibniz algebras, but however, there was no previous study for evolution algebras. So what we first need to know is how Frattini theory is defined in the context of algebras. And in fact, it is completely analog to the case of groups. If the Frattini subgroup is defined as the intersection of maximal subgroups, we will define the Frattini subalgebra as the intersection of all maximal subalgebras. Moreover, we will need the definition of the Frattini ideal, which is the largest ideal contained in the Frattini subalgebra. And we also say that an algebra is phi-free if its Frattini's ideal, is trivial. The first result we obtain using simply these definitions is that if we have a nilpotent algebra, then its Frattini subalgebra coincides exactly with the derived subalgebra. And the case of the algebras is especially representative because the converse of this result also holds, but this is not true for evolution algebras in general. So one of the main mathematical objects when studying the Frattini theory, Lie and Leibniz algebras, is their nilradical, which is traditionally defined as its largest nilpotent ideal. And why is the nilradical very used? Mainly for two reasons. Because the nilradical in the context of Lie and Leibniz algebras is perfectly well defined because the sum of nilpotent ideals is always nilpotent again. And because it has another nice property, which is that its square is always an ideal. So using the result we had in the previous slide, and also using this result I have here of David Towers, it is easy to check that the square of the nilradical is contained in both the Frattini ideal and the Frattini subalgebra. So if the square of the nilradical is different from 0, the Frattini ideal and the Frattini subalgebra have to be different from 0 too. So the nilradical is kind of criterion to decide whether the Frattini ideal and the Frattini subalgebra are trivial or not. When we try to apply this viewpoint to the case of evolution algebras, we find that in general, the nilradical of an evolution algebra, as it was defined in the previous slide as the largest nilpotent ideal, is not well defined in this context, because the sum of two nilpotent ideals is not necessarily a nilpotent ideal again. For instance, we have here an evolution algebra which is non-nilpotent, but where we can find two different maximal nilpotent ideals. So it is a concept that, as I said, it is not well defined. But this doesn't mean that it will never be well defined. And in fact, in our family TK, it is well defined. And moreover, we have it perfectly characterized as shown in this theorem here in terms of the lambdas and also the parameter k. So using this computation of the nilradical, we were able to prove this result here, which essentially gives an equivalence between several properties of the evolution algebras in the family TK. But to sum up, the main conclusion of this result is that it characterizes perfectly both the Frattini subalgebra and the Frattini ideal in this family. The Frattini subalgebra and the Frattini ideal are trivial if the codimension of the annihilator is 2 and it equals the derived subalgebra in any other case. Of course, this is not a general result and we wanted to obtain more. So we decided to propose two possible definitions, constructions of mathematical objects that, in our opinion, capture the notion of nilradical we were looking for. On the one hand, we define the basic nilradical, which is the largest nilpotent ideal, which additionally is basic. This way we get that it is well defined. And it is quite easy to compute because it depends mainly on the upper annihilating series of the corresponding evolution algebra, and computing the upper annihilating series in evolution algebras is almost trivial, so it is very easy. But most of the times offers very little information. On the other hand, we have the super-solvable nilradical, which is the largest nilpotent ideal, which in addition is super-solvable. Well, as you can see, super-solvable is in between quotation marks because we need something a bit stronger than super-solvable, but for this talk is enough. And in this case, we have a more complex mathematical object, which is a bit more difficult to compute, mainly because we have to find all the one-dimensional abelian ideals, and this is not a trivial task in general, but in return, it normally offers more information than the previous option. So to sum up, we have here two options of mathematical objects that are well defined and work quite well, but the first one is simple and more limited, while the second one is a bit more complex but more informative. In fact, we think that the second option captures perfectly the notion of nilradical we were looking for, because of these two properties I present here. First, it works quite well with the sum. If we have any nilpotent ideal and we make the sum of this nilpotent ideal together with the supersolvable nilradical, we get again a nilpotent ideal. And a natural consequence of this result is that if the nilradical in the usual sense is well defined and coincides with the supersolvable nilradical, if and only if the supersolvable nilradical is maximal within nilpotent ideals. But everything could not be good, and one of the main weaknesses of this notion is that in general, the square of the supersolvable nilradical is not necessarily an ideal. And this is something that we have to be very careful with, okay? So it's time to present our main result of this section. And although I have to say that we got better results and we improved it in some specific cases, this is the result on which everything that comes next is built. So I think that it is enough. So if we have a phi-free algebra, then the basic nilradical must coincide with the annihilator of the algebra, and moreover, if the square of the supersolvable nilradical is an ideal, then it has to be exactly the sum of the one-dimensional abelian ideals. So this means that the supersolvable nilradical has to be similar to the abelian socket of our algebra. And let me finish with an example which shows that the converse of the previous theorem is not necessarily true. For instance, if we consider this evolution algebra whose product is E1 squared equals E1 plus E2, E2 squared equals minus E1 minus E2, and E3 squared equals E2. It is easy to check that the basic new radical coincides exactly with the annihilator, and that the super solvable new radical is exactly the only one-dimensional abelian ideal the algebra has. However, it is not phi-free because the Frattini ideal is the span of E1 and E2. And to finish this talk, I would like to mention an application of Frattini theory, which is the study of dually atomistic evolution algebras. An algebra is said to be dually atomistic if every proper subalgebra is an intersection of maximal subalgebras. So in particular, the zero subalgebra has to be an intersection of maximal subalgebras too. So if we have a dually atomistic algebra, then necessarily both the Frattini ideal and the Frattini subalgebra has to be trivial. This property had already been studied in, for example, the context of the algebras, and we have here this classical result from Scheiderer, which says that every dually atomistic algebra is either abelian, almost abelian, or simple over a field of characteristic zero. In fact, if we change the field of characteristic zero for any arbitrary field, it is enough to change simple by semi-simple, and that's it. Of course, we were not able to get a result for evolution algebras as good as this one, but we were able to characterize the dually atomistic property in some specific cases. Of course, one of them in the family TK, where we were able to prove that an algebra is dually atomistic if and only if it is isomorphic to the evolution algebra whose structure matrix is 1, 1, minus 1, and minus 1. And here you have all our articles and preprints in which you can see all the results we discussed here today. Thank you very much for your attention, and I'm ready to answer questions and comments. Thank you very much.
Oh, thank you, Andrés. Everybody can just turn the microphone. Thanks, Andrés. And
thank you very much, Antonio.
Very nice lecture. So, is anybody in the audience have any question? One willing to make any suggestion, Andrés? No? No? I have one question, if I may. Yeah, no hand rising, no? Okay. Oh, Janice is Janice missed the definition of the original Frattini reference, the group theoretical one. So could you please put the slide?
Yeah, of course. Yeah, it is an article from Giovanni Frattini.
An old one.
An old one.
Yes.
Yeah, that one, and it is written in Italian, so
yeah, so easy to read.
Yeah.
Okay, so any other question? Yeah, one more. Thank you. Okay. So I have one question which is kind of related with this parallels you do with the group theory. So when describing the lattice of a evolution algebra, so there is a classical result called Gauss-Sutton lemma. I don't know if you ever heard about that. It's a way of describing. No, it's a way of describing the subgroups of a direct sum of a product of two groups. So it tells you how the subgroups of a direct sum of two other groups.
And you have a product of two groups.
Exactly, right? So not every subgroup of a product is a product of subgroups, but there is a relation in which you project every factor, and then there is some, well, I mean, there is a correspondence. So it's something like the Klassenhaus lemma, like the butterfly lemma. Right? Okay, so if you don't know, then it doesn't make any sense, the question, because I was going to ask whether if you you prove something similar, right? That since you are making a kind of a mimic procedure, a parallel procedure with the group theoretical case.
Yeah, I didn't know that lemma, but I have to say that without knowing it, I've tried to obtain some results. Maybe if we can obtain something when we have the product of two evolution algebras or something like that, but it was completely impossible for me. It was I could not control it, so I don't have conclusions about it.
Okay, I know there
But
is a kind of a categorical proof of it, that if the category is good enough that it's close under finite product and they have a regular epimorphism and some notion of congruence, you can prove a Gaussian lemma. But well, I don't know.
Okay.
I never checked whether evolution algebras are within this framework. Okay. So, any other question? No? Not in the chat? No? If not, then thanks again, Andrés, for this next lecture.
Okay. Thank you very much.
Very nice.
Okay. Thank you very much for the invitation.